Good afternoon, everyone. Good afternoon, good morning, and good evening from wherever you are joining. My name is Mohammad Zakir Hossain. I work for AIT Extension of Asian Institute of Technology. Probably those of you do not know about AIT Extension. Let me just briefly tell you that AIT Extension is the executive education and professional training arm of Asian Institute of Technology. We are basically mandated for taking care of professional and executive education and consultancy and the research work at AIT. So this is a great pleasure and of course an honor to welcome you all to this hybrid seminar on low light imaging of the Earth at night. And today we have a distinguished speaker with us, is Dr. Christopher D. Elvis, who is coming from the Earth Observation Group at the Colorado School of Mines from United States of America. So before I begin, I think I just would like to talk a little bit about this seminar. I think we have been sharing the information briefly about this, mainly with the title. So basically in this seminar, Dr. Christopher will talk about the 3 global products from the night light data collected by the NASA and the NOAA visible infrared imaging radiometer suite instruments, which are basically lights at the Earth's surface, boats carrying lights, and fires and flares. He will also go through a deep review on the VIRS low light imaging capabilities, example of the data products, and a new global infrared emitter explorer web map service. I think those of you who have attended our online sessions or online hybrid seminar before, we will have this seminar roughly for about an hour. I will just briefly tell you about the tentative schedule of this seminar right now. So immediately after I finish my introductory words, I will request our executive director, which also the executive director of the UNITAR CEPHAL, will say a few words and welcome our speaker to start the seminar. And after his words, I will also introduce briefly Dr. Elvis a little more, and then we'll invite him to start his session. And it will go for probably roughly around 30 to 40 minutes maximum. So after his deliberation, we will have time for the question and answer. We will try to make it within 10 minutes. And after the question and answer, we will go for the final part, which is kind of conclusion and giving thanks to all of us. For you, those are joining from this wonderful place, which we are calling the Creator Space at the Entrepreneurship Center at Asian Institute of Technology. You are all welcome to join this session. Those of you who are joining online, please make sure that whatever questions you have about this session and about AIT Extension, about UNITAR and CEPHAL, please use the Q&A box to put your questions, and we will try to make sure that we will bring all the questions to the speaker and to other colleagues to try to address and answer those questions. The people or the participants who are joining physically, attending this seminar, of course, you will be allowed to ask directly question to our speaker. So with that, once again, let me welcome you all to this hybrid seminar, which is actually jointly brought to you by AIT Extension and UNITAR CEPHAL. Let me just once again talk about UNITAR CEPHAL and AIT Extension. As I have just mentioned, AIT Extension is the executive and professional education arm of Asian Institute of Technology, whereas the UNITAR CEPHAL is a center at AIT. UNITAR stands on United Nations International Training and Research, United Nations International Training and Research Center. Under that, we have the CIFL Center, which is basically a center for international training for local actors and local leaders. We have the executive director to talk a little more about that. So as I just mentioned, these seminar is actually brought to you by AIT Extension along with UNITAR CIFA. So I think with that, once again, I'd like to welcome you all. We will keep this open so that participants keep joining our program from now until the end of this session, which is probably going to be 1 hour. So now I'd like to request our Executive Director, Mr. Voraved Chonlasin, who is also the Executive Director of UNITAR CIFL Center at AIT, to say a few words about this session.
Allowing me to meet you this time. I personally interested in these topics and also meeting you in myself so that we can explore the way that how we are going to work together. And thank you also for coming to AIT and also contribute to AIT on the new technologies to our students, and also our staff and also researchers in AIT. At the CIFA Center, as Dr. Saki mentioned, so our jobs, this is a sister center in AIT, extended capital on behalf of AIT. Our job is to bring the new knowledge to the CIFA members of the 31 members around the world. And with these 31 members, including the one in Bangkok, which we are looking after, is going to reach out to the audience within the 31 members around the world. So we are hoping that what's going to be giving presentation by Christopher this afternoon are going to be heard by members of the members in the also networks. Importantly, UNITAR is very also much focused on the innovations and technologies in this at this point of time, so that it is really adding values to what AIT is doing, AIT CIFA is doing, and also people at AIT is doing, and also academic environment is doing. So thank you so much, and we are going to have the same similar events continuously, and we are looking forward to your interesting knowledge of these emerging technologies that the world is doing. Thank you.
Thank you very much, Mr. Voraved Chonlasin. I think now it is time to introduce our speaker, Dr. Christopher D. Elvis. So before I do that, I like to just recall our memories that we have been working with Dr. Christopher D. Elvis since 2022, more than a year. Initially, we started with a seminar like this back in 2022. And then, of course, this topic got really interested by AIT people, especially the researcher and the students, and also the departments here, which is the remote sensing and GIS field of studies at AIT. And we know that now Dr. Christopher D. Elvis is back, and also he's teaching a credit course at remote sensing and GIS field of studies. We are very happy with that. We make this relationship, and the relationship we hope that will go ahead. So just to talk a little bit, our distinguished speaker today, Dr. Christopher D. Elvis, is having a PhD in applied art science from the Stanford University, and he did his PhD back in 1985. Since then, he has worked for a number of well-known and very distinguished organizations, namely NASA Jet Propulsion Laboratory, and then the Desert Research Institute. And then he also had worked for US Environmental Protection Agency, and finally he also worked for NOAA. So I think he has retired. He has retired from NOAA in 2019. And after his retirement, he moved all his laboratories and the people to this Colorado School of Mines, and he set up this laboratory called Earth Observation Group. And I think since then he has been based there, and he has been working more on research and also in teaching. And that's how we came to know each other. And we were very fortunate to have him here today again to talk about this very important topic that is known as low light imaging of the Earth at night. So with that, it's time to invite Dr. Christopher. And maybe, sir, if we have missed anything to introduce yourself, please add to that. And then, of course, you can start your session.
Okay, great. Thanks so much for the introduction.
Yes.
So I started working in this area in 1994, so 30 years. And we pioneered the development of global maps of nighttime lights, originally using a relatively crude instrument called the Operational Line Scan System that was flown by the US Air Force's Defense Meteorological Satellite Program, DMSP. And it had 2.7 kilometer ground sample distance from pixel center to pixel center. It had low light imaging and a thermal band. And believe it or not, we work with 6-bit data. And so it was really far, and it had no calibration. And so it was really by far not very good data, but we made a lot of products and there were a lot of users and a lot of papers. And then in 2012, we got a much better instrument. So I'm going to show you what this low light imaging data looks like. And then we're going to go look at some of our web pages and some of our where we provide data access, and then some of the data products themselves. So we're talking about lights at night. And of course, there are, we're quite familiar with the lights from cities and towns, but there's also lights in industrial facilities. And in some cases, not only lights, but infrared emitters. There's gas flares, there's biomass burning, and there's lights on boats. Now the VIIRS its primary mission is weather. And so the meteorologists set the requirements. It collects 14 orbits a day. It's in a polar orbit. So it's going around the Earth in a circle from North Pole to South Pole and around. And the Earth is turning underneath of it. And so that provides the forward movement of each orbit until you get 14 orbits in a day. The swath width is 3,000 kilometers, and it collects beautiful imagery. Here's a daytime image of shows the Korean Peninsula and parts of China, and these beautiful storms. So it's really fantastic data. It's pretty coarse spatial resolution. It has about a half-kilometer spatial resolution pixel footprint at nadir, and that expands to about almost 3 square kilometers at the edge of scan. So as you go out, most of the spectral bands, you get larger and larger footprints. Now, one of the unique things about VIIRS is that it collects low light imaging data using a broad, what we call a panchromatic band from 0.5 to 0.9 microns. And it uses time delay integration to amplify the signal. And this was built in. It's called the day-night band. It's built in to meet a requirement from the meteorologists who want to see clouds at night in the visible, because they knew since the 1970s that they could do a better interpretation of weather and predict weather better if they had at least one long wave infrared band and then a visible band alongside of it. And they had that during the day, but they didn't have it at night because the instruments that they had back then had no amplification of the visible band signal at night. And so they asked the engineers if they could design an instrument that could see clouds at night in the visible. And the solution the engineers came up with back then was a photomultiplier tube. And that amplified the signal to a level where you could see clouds at night if there's some moonlight. When there wasn't any moonlight, you still couldn't see the clouds. But here's an image that shows, so this is on a night with some moonlight, and I can tell that because there are clouds. There's clouds over here and over here. This looks like fog. And so with a million-fold amplification of the signal, in addition to moonlit clouds, the instrument detects lights at the Earth's surface. And here's lights from Manila. And if you look around, you can find other spots of light and even a trail that goes down south of Manila and over to a place called Lucena. And so when we started working in 1994, we worked from scratch, building the algorithms to take a year's worth of this type of data and make a global map, cloud-free composite of the nighttime lights of the Earth. So this is one of the low-light imaging bands on VIIRS. It's the most famous one. So the VIIRS is very unusual in that it collects four daytime channels at night. It collects two near-infrared. There's M7 and M8 in the near-infrared. And then there's M10 and M11 in the shortwave infrared. And so when there's no sunlight, these bands serve as super detectors for infrared emitters. And so you can see the noise floor in this band, and you have to look more careful to see the noise floor in the other bands. But basically, the image is recording the noise floor, and it's punctuated by bright pixels where there's infrared emitters at the Earth's surface. And it still has detection limits, but this is far superior to the traditional use of midwave infrared for detection of fires. And what it allows us to do is to detect smaller fires in smaller industrial sites. And we have enough spectral bands that we can model the Planck curve, which allows us to estimate the temperature, the source area, and the radiant heat. Okay, so actually EOG was founded in 1994, and we got the VIIRS data in 2012, and I retired in 2019 and moved my staff, my algorithms, everything to the School of Mines. Now, here's how we get the data. The satellite's in a polar orbit, and it has a solid state recorder on board. And when it goes over the North Pole, it plays the recorder back to ground stations that are in a place called Svalbard, far north of the Arctic Circle. And the data then go by undersea cable to NOAA's National Satellite Operations Facility, NSOF, in Suitland, Maryland. And they take the raw data and geolocate it and convert the original counts into radiances and provide that to the National Weather Service. That's their primary customer. Now, the program office recognizes that there's a lot of other value in this data, a lot more value other than just weather. And so they have a data pool, and we're registered to access the data from the data pool. And we usually get the data about 2 hours after it's first collected. Okay, so we already mentioned the data products. We've got VIIRS nighttime lights, VIIRS night fire, and boat detections. And we have temporal increments of nightly, monthly, annual, and multi-year. And currently, we ingest and process 150 gigabytes of nighttime data from each VIIRS that's flying. Currently, there's 3 of them. Okay, so now I'm going to switch to a look at our website. Okay, this is this is the homepage for our group. And so you scroll in a little bit and you see these 3 buttons here that go to our 3 products. So I'm going to take a quick spin through these so you know where to get the data. The nighttime lights data is free. It's not copyrighted. The You don't even have to tell us what you're gonna do with the data. Of course, we vastly appreciate getting some attribution such as data supplied by Colorado School of Mines or citing our papers, but we've got various many timelines. And so we have over here, here's the product sets. We've got monthly, annual from version 1, which was just for a couple of years, then annual from version 2, which goes from 2012 to 2022. We're going to start working on 2023 very soon. We've got nightly mosaics and then nightly temporal profiles. And so if I go over here, this is the version 2 nightly products. And so if I go over there, it's broken up by year. Oh yeah, version 2.2 has 2022. So if you go and look at one of these directories, you see the different file types. And so the best file type is here, the average mask, because we've made a cloud-free composite that's still got noise, fires in it. That's here, average. And then we have a lit grid cell mask that we make for each year that shows the area where we detected lighting. And so this is the most cleaned up. And we have to do quite a bit of work to get the aurora out as well. So that's what that looks like. And so there's a lot of different data types for nighttime lights. Let's go look at one of the others. There's Beers goat detection. And so here we have a data download site. Oh, okay. It's over here, data download. And so we have a navigator and a repository. And so let's look at the navigator. It shows a map of the world, and you can pick an area of interest. For instance, let's go up a little bit, Oceania, Southeast Asia. So we have service areas. And so we lump Thailand and Cambodia in a single service area. And there's that golden line is the outline of the EEZ for Thailand and Cambodia. What you actually get is a rectangle that covers this entire area. And you can look for daily data. And so there is daily data up until yesterday. And if you look at that, there's data for 3 satellites. And but honestly, I usually go global. And so here again, we've got data from 3 satellites. So that's Beers goat detection. We're going to look at last night's data in a few minutes. So let me go back and show you the third data type. Here's night file. Down 1. And so the operational product is version 3. And so it has, it's broken up into months. It goes all the way back to December of 2017. To get the older data, you have to go to version 2.1. Well, I thought that was where it would be. There is data that goes back to 2012. I think this is it. So yeah, it goes back to March 2012. And so if we look at one of these directories, let's go back and get the version 3, which has the recent data and January. And so here again, we've got data from 3 satellites every month. And the satellites are about 50 minutes apart in terms of their overpass. And they start about midnight and they end about 3 o'clock in the morning. And we've got a KMZ that you can look at in Google Earth, and an easy CSV that has a subset of the columns in the full CSV. And so this data the VNF data is licensed. The licenses are free for academics and nonprofits, governments, but we have an income stream from commercial users. And so if a company wants to use the data, they can, they just need to pay an annual fee. But for researchers, it's free. And we're going to look at last night's data for this one as well. So I think those are the three data products. Now I'm going to go to, okay, so I've got a lot of things loaded up here. I'm going to start turning some off just to remove the clutter. And we're going to start looking at the Beers Smoke Detection product from the most recent new moon. The Beers Smoke Detection product is the detections drop down to quite a low level under the full moon. And there's a couple of reasons for that. The fishermen that are using lights to attract and catch know that under the full moon, they're competing against the moon for the attention of the fish. And so a lot of them just decide, well, I'll go to port, dock, resupply, and then I'll go back to fishing after the moon wanes. The other reason is that to prevent false detections on moonlit clouds, we have to raise the detection threshold. We have a way to do that adaptively. And so the threshold rises and falls based on the cloud, the reflectance features on the clouds. And we've got that worked out quite nicely. But I'm always amazed at how many boats there are detected in this part of the world. It's staggering. These are all boat detections, and they're sized based on the size of the place mark. So the really big blue ships, those are the brightest ones. So let's take a look at this one. It says it has a radiance of 228. And we see radiances up to 1,000 or more on some boats. And from our field experiments, we know that 1,000 kilowatt light bulb with no shielding results in about a single radiance heat. And so that implies that this boat, okay, so this implies that this boat is carrying about 228,000 watts of lights. And it's known that some Chinese boats carry 500,000 watts of lights. Now let's look at the other end. There's small boats. It's the smallest one. And it has a radiance of 3.7. And we see radiances down to about 0.5. And so we do that sorting, give the different detections different place marks and different sizes of place marks. So the best detections are the blue sailing boats. The reds are gas flares. The platforms are white. And then there are persistent detectors, persistent sites that are little white triangles. And I don't see any handy. Then the weak detections are a set of concentric circles. So we try to embed that in the into the KMZ, because we know a lot of people, that's where they start. But they can also download the CSV, which has the tabular form of the data. Okay, so that's on a nice moonless night. Let's go look at a night where there's moonlight. This is from last night, and you recall there was huge clusters, clouds of detections from in the new moon data. And but let's take a look just to confirm that we're detecting data from last night. Here it says local time 2024 01/24. Yeah. Okay. So what I showed you is that these detections are from this morning. you can read the local time, 2024-01-24 at 2:22 in the morning. And so we have, this data was ready as early as 6 o'clock in the morning local time. That's when we try and set out alerts. And we have an alert for both the fires and the boats for the Thailand region that we send out to a subscription list. And if you want to be on that list, I'm happy to add you. You just have to be ready. You'll get a couple more emails every day. Okay, so that's the boat detection stuff. And now let's look at the fires. Okay, now these are color coded based on the temperature. And so the coldest temperatures are purple. Okay, so I'm going to go find some bigger fires because I want to show you. Okay, so let's go look for some really big detections. And so I'm going to zoom out and then zoom back in because I want to show you what we do with the plank curve fitting. And Africa is usually a good place for big fires. So let's go there. Okay, I see one down here. So these are color coded. And so the coolest ones are purple. This one's blue. And now you can see the plank curves. And so we have, here's wavelength on the x-axis and radiance on the y-axis. And you can see these red asterisks. Those are the detection bands. And so one of the really great things about those daytime channels is that with sunlight eliminated, we can attribute all that radiance to the infrared emitter. Here's the background, which is primarily driving the radiance in the long wave infrared. And we fit two Planck curves. We fit a Planck curve to based on for the hot object inside the pixel. It's a subpixel hot spot or hot area, and then a cool background. And that makes it possible for us to apportion the radiance here in the midwave infrared because it's got a contribution from the background and a contribution from the infrared emitter. These short wavelength channels have essentially no contribution from the background. So they're very clean, and we drive these Planck curves, and this Planck curve tells us a lot about the hot object. We can find the peak wavelength and then use Wien's displacement law to calculate the temperature. We have these subpixel hotspots or subpixel emitters. They look like gray bodies. And so we can get their temperature from Wien's law, and then we calculate the Planck curve for an object that temperature that is completely filling the field of view. And it's a hypothetical pixel that you won't ever really find one, but we use the amplitude of that Planck curve compared to the Planck curve, form a ratio, and apply that ratio to the pixel footprint. And that allows us to estimate the source area. Then we take the temperature and the source area as input to the Stefan-Boltzmann's law, and we calculate radiant heat, which is in megawatts. So that's our fire product. Now let's go back. We looked at the boats. Okay, next thing I should do is show you our web map service. So did the screen move? Okay, very good. And so we've taken 10 years of this FEARS night fire data and composited it, filtered out the fires, and found as many industrial emitters as we can. And they're color-coded. The red ones are gas flares, but there are steel mills, there are coal mines, there's landfills. In total, there's about 20,000. And we'll go look at one that I'm familiar with in the South China Sea. Let's see if I can pick it up. Okay, so I put the cursor on the location, and it tells me that the average area in an observation is 7.5 square meters. The temperature is 1765, which is about twice as hot as biomass burning, and that detection frequency is 96% over that whole time period. So this is a really steady flare. And so let's go look at, oh, I guess I got to click on it, really click on it. And we're calling it an upstream flare, which means it's in an oil and gas production area. And then we have a super resolution image. And so we do our initial search in 15 arcsecond grid space, we find the candidates, and then we build a super resolution image of this infrared emitter. And we work with the actual center lat longs for the individual pixels. And doing that, we can see if there's a cluster. And so here's a cluster. This is the super resolution image. It's rendered at 100 square meters, and you see a little square. That is actually a representation of the pixel footprint, cumulative pixel footprint for this emitter. And also we show that we call it a single emitter. So this is the classic case where there's a single emitter. Let's go look at a place that's a little more complex. Okay, so here we found two emitters. We found this one, and then there's something up here. I don't know if it shows up in the screen, but we found two emitters. And so let's go back to the other one because I want to show you the temporal profiles. Okay, open temporal profiles. And so now you can see the temporal profile that goes all the way back to 2012. The top panel is the radiance in M10. The middle panel is temperature, and you can see the temperature has been pretty steady at about 17.5, 1,750 K. And then we also calculate a temporal profile for the flared gas volume. And so this is also, you would have to get a license that's available for free to access this. We also have aggregated profiles that are for different types of emitters. Let's look at steel in China. Well, yeah, so this is monthly data, and the blue posts are cumulative radiant heat, and the red line is number of active sites. So the active sites scale is on this side. And so you can see there's a big jump at the start of 2018. And that's when we got the M11 spectral band. And so during the early years, we only had 2 near infrared and 1 shortwave infrared. And we got the second shortwave infrared channels, and we were able to vastly increase the number of detections where we could calculate temperature. Because if there's only detection in a single spectral band, we can't calculate temperature. So I think I'm going to wrap it up here. We can have some questions and discussion. So thank you.
Thank you very much, Dr. Christopher. I think the floor is open now, and before we go to the Q&A box, where I see still no question, maybe the floor is now can be open. So the colleagues and participants and our students who are joining from this room, could you? Yes, I can see one hand raised. Maybe the other can construct your question by that time. So yeah, please.
Yeah, thank you, Dr. Christopher, for your presentation. I just wonder about how this VIRS can detect the temperature, because, like for example, in the atmosphere, the land temperature, atmosphere temperature, it's going to be different, right? How this sensor can, in which column of atmosphere that this temperature is being estimated?
We're actually working with the top of atmosphere radiances.
Okay.
And so if you look at the Stefan Boltzmann's law, which predicts the radiant output by wavelength,
Mm.
there is a term there for temperature to the fourth power. And what that does is when there's an infrared emitter, it is very obvious because the normal temperature of the Earth is down around 300 K. And the temperature of the flare is 1800 K. And so there's a huge boost in the radiant output. That's what makes it possible to spot those pixels. For the newest version of VNF, Beers Night Fire, we apply an atmospheric correction. We didn't use it at first. We're going to have to reprocess. But the atmospheric correction doesn't change the temperature very much, just a little bit. Where it really affects is the radiant heat, which is what we use to index the flared gas volume. And so we know that our numbers for flared gas volume in Nigeria are going to go up, and probably the numbers for Algeria, which is very dry, are probably going to come down because the atmospheric transmissivity, particularly in the midwave infrared, is much lower in Nigeria than Algeria. So it's, the whole key is that T to the 4 term, temperature to the fourth power, because that gives a tremendous boost to the radiant signal for the pixels that contain infrared emitters. And so the background is, even cold clouds only get to around 250 K. They're cold, and the land surface is somewhere around 300 K, but the flares are 1800 K. And they stand out very clearly. And we can see that we get good Planck curve fits. And so I think it's clear that we can calculate the temperatures for infrared emitters. The other thing that's very important is that we have multiple spectral bands. And so I didn't show it, but in M11, which is the longer wavelength shortwave infrared, and M12, which is the first midwave infrared, there can be saturation. And so we have enough spectral bands that we can use those other bands to identify the pixel the band that is affected by saturation and exclude it from our Planck curve fitting and still get a good estimate of the temperature.
Okay. Thank you for your answers. Now I understand about, like, it's because it's like a different the different columns, and also like because there is like the different temperature between the land itself and also the flare, so you can take up this threshold. Is it correct that I'm on?
Yeah. Well, at midwave and long wave, you can see to the Earth's surface. And you might be looking at a cloud top, or you might see the ocean surface or the land surface. And so at those wavelengths, you can see to the ground. And there are people that calculate the temperature of the Earth's surface and clouds. And they can do that because those types of surfaces either completely fill the pixel footprint or they come pretty close. And so our case is different because the infrared emitters are just a tiny fraction of the pixel footprint. But because of that T to the 4 term, they've got a punch in terms of radiant output that makes them easy to spot. Of course, there's still detection limits for biomass burning. I think our detection limits are around oh, 10 square meters. But for flares, because they're hotter and you've got that T to the fourth power term, it gets down to less than a square meter for detection limit for flares. And did that help with the question?
Yeah, no. I understand the concept now. But another questions, like for example, it's not talking about the flares, but it's more talking about the lights that detected in the sensor. Like for example, the lights in the urban area, it has high intensity, right? But for example, in the rural area, it has lower, and it might be different as well in the different countries.
Oh, yeah.
Yes, and how in this sensor, did you normalize the range of the lights, or do you make like a baseline based on region? I just wonder about setting of the baselines. If actually,
Yeah. Okay. Well, let's look at some actual image data from the nighttime lights. This is zoomed in on Bangkok, and it's 3 different years. And so we've got 2022 in red, 2017 in green, and 2013 in blue. Now I can adjust the contrast. Let's do this. Okay, well, let's try another one. Yeah. Okay, that's too dark. So let me try. All right, now you've got a beautiful image of Bangkok. And if we look at the radiances, let's get a tool. Let's see, look at this one. So if you go to the center of Bangkok, the radiance is, oh, there, that looks normal. You've got in 2022, the radiance is 33, 27 in 2017, and 32 in 2013. But if we go out into the countryside, it's much lower. And so we do our best to detect the dim lighting, but we know that there's detection limits. And part of that is that we're building global products. And so we provide the users access to the source data that we use to make our global cleaned up nighttime lights product, global product. If someone wanted to, they could go back to those source files and make their own discrimination of what's lit and what's not lit. And so occasionally we see somebody that does that in paper. We end up losing some features because they're relatively dim. The classic case is a lit roadway, and it'll drop out because we're having to set our thresholds for discriminating lit versus non-lit at a level that works globally. Let me find an example. I've got another image here. Yeah, okay. Where'd it go? Okay, so now these are a pair. The one on the left is the source image, and I'm going to move over a little bit to a place that I looked at in my class today that has some roadways that disappeared. So let me see if I can find them. Yep, I think there's some here. So let me go adjust the contrast and we'll take a look. I think there's a roadway in here. You're seeing the images on the screen? Yeah, okay. Well, let's see. Well, I'm drawing a blank here, so let me go. Okay, so here's my, oh, it's image 1 that has it. Okay, the link's broken. Let me go back. Link, unlink, link displays. We want 1 and 2. Okay, now. Okay, so on the left is the original average that still has fires in it and background. And so you can see there's signal, very low signal, even in the areas that don't have any lights. So right there, it says it has less than 1 nanowatt, down around 0.2, 0.18, 0.04. And so we want to zero out that background because we know that lots of people will sum up the lights in their area of interest. It could be a whole country or a province. And if we don't zero out the background, then in some cases, their results are dominated by the background. The classic case is Afghanistan, where the background dominates. There's just a few towns that have any lights. And so if you sum up the raw average, it's dominated, your temporal profile would be dominated by the background. So we originally, we just posted these raw images and without zeroing out the background. And we heard back that a lot of users were using the data in such a way that zeroing out the background was important. And then we've also have fires. Well, let me try and get a better contrast stretch on this. Come on. Okay, that's fairly good. And so we do outlier removal actually by using the median. And so the median will drop out the biomass burning because they're ephemeral. They're extremely bright, but they're not typical. And so we use the median to knock out the outliers. And then we use a data range index to identify background. And because we're setting the threshold on that data range for global, there are a lot of lights that, well, it's these dim roadways that drop out. See if I can show it to you. Okay, so this is a classic case. You can see it clearly in the original raw average. Roadways. But when you go to our cleaned up product where we've gone to the effort to knock out the fires and zero out the background, a lot of them get lost. And I would dearly like to bring them back. And we had a student work on that last summer and they didn't finish. And so it's still on our list of things to do. And we're happy to collaborate with other teams to find a way to bring back the very dim features that you can see visually, but because we're trying to clean it up for a global product, we lose some features. What else?
I think that's all. Thank you.
Thank you, sir. That's been a very powerful knowledge sharing session. I just have one very interesting thing that I see today, sir. When you show us the super resolution image, so this is very interesting for me. Upon creating the super resolution image from the VIR's derived products, which were originally at, I believe is 500 meter spatial resolution, how do you come up with something that is more finite in terms of resolutions, which is more than 500 meter? And if we're doing more fine spatial resolution, what are the baseline images that we should use? Because the baseline image is going to be very important in terms of capturing the texture and also.
To answer that question, the answer is simple. When we make, for instance, these global products that I have on the screen now, it's on a 15 arc second grid. And so the original pixel, we're given the latitude and longitude of the pixel center. And the pixels don't fall in the same place over time. They kind of skew around. And so we're taking a group of pixels within that 15 arc second grid cell. Over time, it starts to fill in with detections. But in the super resolution, we never go to the 15 arc second grid. We use the latitudes and longitudes, original latitudes and longitudes for the individual pixels. And we actually do the analysis with a cloud of pixel centers and determine whether there is a feature there, a dense cluster, and then that confirms that there's an infrared emitter there. And then we evaluate, is it a little square? That means that there's a single emitter. And if it's got some distorted shape, that means that there's several emitters there. And we try and break it up into 2 or 3 segments. So that's, and we had never thought about super resolution for many, many years. And then one of my staff showed it to us and we said, wow, this is going to help. Because we use the 15 arc second grids to get the candidates that we think could be industrial infrared emitters. And then we switch over to the super resolution mode to see what's really there. And so it's a really valuable way to work with your data. There's a lot of groups, you know, mine included, that make extensive use of uniform grids like 30 arc second or 15 arc second, but you lose some of the features and some of the information content when you take pixels and you use the pixel centers to drop them into the appropriate 15 arc second grid cell.
Thank you, sir.
So I'm looking at my back. Any other questions?
Oh, so one thing, as you mentioned, when you take this 15 arc grid cells, the pixel center, and then you created a super resolution image, is my hypothesis, so is my logic correct? Are we losing any sort of temporal relation amongst this kind of event?
Well, you know, for the super resolution, all we've used the 15 arc second grid cell product to do is to identify the candidates. So there are clusters of 15 arc second grid cells that have some additional brightness in some of the spectral bands that they trigger the Veers Nightfire product. And so it really is a crude looking feature. And so we take the outline of that feature and draw a vector, and then we go back to the original pixels and get the precise latitudes and longitudes and build a data cloud that it's been untouched by the 15 arc second grid. And so that's where we get the most clearest view of the feature.
Thank you, sir.
Dear participants attending online, would you like to raise your hands? Because I haven't seen any question in the Q&A box so far. Dr. Please, maybe I can ask one or very basic question. I'm more interested about the port detection. And, it was really fascinating to see your visualization, where I see probably thousands of boats are gathering in the Upper Gulf of Thailand, in Cambodia side, and also the Vietnam Chinese side. Is there any possibility that we can actually differentiate from this data, the different kinds of boats?
Well, the only thing we've got is the brightness. And here is our multi-year product for the Veers boat detection. This is out in the South China Sea. So let's see if I can get closer to Bangkok. Okay, so here's in the Gulf of Thailand. And there's something unusual going on here. Okay, well, let's try and adjust the contrast. Oh, okay, so I have to go turn off a switch here. Go to vector parameters, turn this off, and then I can move the cursor and get a better contrast stretch. So we're going to look in the Gulf of Thailand, and this is a new product. We used to make nightly products, and now we've got 10 years since 2012. We've got 11 full years of nightly products. And so what we did was to basically lay them on top of each other. And we were expecting we would see fishing grounds because we designed the algorithm for fishing boats, but we see other types of lights too. Platforms, anchorages, transportation corridors. And in the Gulf of Thailand, there's something that I've not seen anywhere else in the world. Can you see the grid pattern?
Yes.
Yeah, there's no place in the world. I've looked all over this product. This is a 11-year accumulation of boat detections. And so it is not a uniform grid. They're actually segments. And you can see some lines delineating different blocks. And so it's one of my ambitions to figure out what's there at the center that is attracting the boats. And I have a hunch that it's an anchored buoy that is acting as a fish aggregating device. And the fishermen know if they go up close to that buoy, they'll have better fishing. And so that's just a guess. It's still a mystery as to who would build such an extensive network. Anyway, this is an amazing product. It hasn't been released yet. I'm working on the paper. I had to start on it in October, then other things got in my way, but I'm going to get back to it. So let's go look at a couple of other places that show interesting features. There's one right here. Okay, this is in the Arafura Sea in Indonesia. And you can see there's a cloud. That's a fishing ground. And so we can use this data to actually delineate fishing grounds and to build temporal profiles all the way back to 2012 for either the entire fishing ground or some part of it. Now, this is shallow water, and in shallow waters, there are often spots where the brightness is higher. So let's take a close look. Here is my zoom window here, and we'll go look. It says that there were, oh, this is in percent. So it says 6.3%. And then off that, it says 0.2%. And so there's definitely something at that spot that is producing light that is getting detected more frequently than the areas around it. And you can see it's not moving, or it's not moving much. It's very steady. And so here's another question. What is it? What's there? And I showed this to some people that work for the fishery agency in Indonesia, and one of them speculated that he used to work out in this area, and they had anchored vessels that provided supplies and cooking, had a kitchen and a restaurant, and it would just park there and provided those services, and they would have their lights turned on at night. And so that's one option. It could be a platform. It could be a
Nighttime hotel, restaurant, nighttime restaurant.
could be. And another option is that could be a gas flare on a platform. Now, we have a separate gas flare product, and so we can find those and label them. And then the lit platforms, that's an option. There are also boats that have lift nets that use lights, and so they're either anchored or they are have posts that go into the sediment. It's more typical in very shallow water where you can build a platform that has legs that go into the sediment, so it's stable, and it has a platform and a roof, and they have typically a hole in the center, and they use floodlights to gather the seafood. They drop their lift net and wait for the cloud of sea life to accumulate in the lift net, and then they pull it up. And so there again, that's going to show up as a platform, a fixed location source that is there vastly more often than the detection of fishing boats spread across a very large fishing ground. So yeah, it's a fascinating product. Let me show you another place that has a lot of interesting things going on. Here is the Yellow Sea, and let me adjust the contrast. I'll put it over here. Okay, so you see the straight lines. That's going from one port to another, and I believe it's a passenger ferry route that continues to run after midnight. And I've ridden on some passenger ferry boats. It's a lot of fun. But you know, after 7 or 8 hours, you might be ready to get off. But they usually have lights turned on. And so I think these are passenger ferries that are going from port to port. But then there are these square features. Those, it turns out, are anchorages. And so they're common around ports. And it's basically a parking lot for boats that are carrying product, either to or from a port. And when the port says, we're not ready for you, they tell you a place that you can go anchor, and we'll call you when you're ready. You can come into port. Now, let's go a little bit further in.
This is a composite image. Correct?
Yeah, this is a 11-year
11
composite. Okay, well, I'm fishing around here. Let's see. Oh, I know where to go. Let's go down to Singapore. Almost there. Okay, so I'm going to expand this because it's really pretty interesting. So let me move it one more time. Okay, so there are anchorages associated with Singapore. And so here's some of them. But look over here, you're seeing transportation routes going through the Straits of Malacca. And then there's a path over here as well. And then out here in the, trying to remember, this is the Natuna Sea. And so you can see these spots here that could be lift net platforms. I really don't know. But there's a lot of interesting things in this cumulative boat detection product. When we built it, we thought we'd get outlines of fishing grounds, but there's a lot more. And so it's going to be a paper that gets submitted in the next couple of months, and then we'll make the product available at our website.
Good. I was just wondering, like, what is the lowest amount of light that this sensor can detect? Like,
Yeah,
like
well,
5 watt, 10 watt, 100 watt,
1,000 watts.
1,000 watts.
Yeah, 1,000 watts. And so the way we researched that was because we had a couple of projects funded by U.S. Agency for International Development, USAID, and NOAA to develop this boat detection product and services such as the alerts. And so the fishing boats typically use large metal halide bulbs, and they're huge. They're like the size of a football, and American football. So they have strings of those lights above their deck, and they have zero shielding. And so what they're actually trying to do is throw up as much light up into the air as they can, because they know that some of it will come back into the sea and create a brightness gradient that leads sea life to the boat. And so the more light they can throw up, the larger volume of water they can harvest from. And so there's an incentive for them to put on more and more lights. And some of the Chinese boats are just staggering. They have 3 levels of strings and a 500 1,000 watt or 2,000 watt light bulbs. But what we did was we got a set of 4 lights, and we built a frame. They were 1,000 watt lights, and we set them so that they're hanging vertically like they do on the fishing boat. And we had a portable generator, and so we would fire them up about 15 minutes before the Veers overpass. We have a predictor, so we can put in a lat long and estimate when the overpass will occur. And so we time these sessions to coincide with detections. And then the next day we'd go and look for the light. And we could vary the number of lights that were turned on from 1 to 4. And we do this in very dark places. We did this at a lake away from the city in Colorado. And then we did it on a boat in the Philippines. And what we learned is that you can get a detection down to about 1,000 watts. It has to be exposed to the sky. So shielded lights, like most street lights, or lights shining out of a window that aren't got directed up in the sky, you're going to have more watts. But the ideal case, yeah, about 1,000 watts.
And what is the temporal things like? How long it has to be there in order
Yeah.
to capture it?
Yeah, well, I wrote a paper on the collection time
Mhm.
for an individual day-night band pixel,
Okay.
and it's between 2 and 3 milliseconds. And it depends on where it is in the scan. So if it's at nadir, it's about 2.3 milliseconds, and at the edge of scan, it's about 2.8 milliseconds. And a single scan collects 16 lines at a time, because the instrument has a telescope that spins in a circle, and every time it goes over the Earth, it collects 16 lines of data. And so that's called a scan, and the time from one scan to the next is 1.7864 seconds. And so we know what those times are. One of the interesting findings that came from that study is that with between a 2 and 3 millisecond collection time, the day-night band is affected by alternating current flicker, which is typically has a cycle of 8 milliseconds. And so it's far from ideal as a detector of flicker, but yeah, there is some flicker effects on the radiance in the day-night band. And the fishing boats do flicker, but they don't necessarily stay in the same place over time.
Thank you. Dr. Chris, we have got some questions in the Q&A box now. So the first question is from Uti Nan. And the question is, do you have a problem with the light from aircrafts? Does it interfere with the lights in the sea?
Do I have a problem with what?
From the lights from the aircrafts? Is there any interference?
What is it?
Do you have a problem with the light from aircrafts?
Aircrafts.
Yes.
Oh, yeah. So that's an interesting issue. So we have a place where we've identified lights from aircraft. So it doesn't happen very often, but there's one place where it's quite noticeable. So let's see. It's up here. Let's see if we see any trace of. Oh. Well, I know where I can see it. If I go to my PowerPoint.
It knows the whole world.
Well, it doesn't show up very well, but there's a series of parallel lines that arch across the North Atlantic. There's 10 paths, and we spotted that, and we wondered, would fishing boats make that? And we decided, no, I don't think so. And so we thought about it, and finally we traced it back to the air traffic controllers on either side of the Atlantic. There's so many flights, and they all arch up far north to get the the shortest route. And there's so much traffic that the air traffic controllers have a stack of paths that aircraft are assigned to. And they might say, go to number 3. And then they've got a path they want you to stay on. And so our next question was, well, are the lights on an aircraft bright enough to get detection? And we thought, probably not. And so then we looked at what was the lunar state when those detections occur. And it's all under a full moon. And so we came to the conclusion that the Beers boat detection algorithm was picking up on aircraft based on the reflectance of moonlight from the fuselage and wings. And so there is one definite feature where we can point to and say, yeah, this is aircraft. Now, it probably happens in other places, but it doesn't happen often enough that we get a distinct feature. And so the North Atlantic, there is, and it's partly because the number of aircraft that fly that route, and also because air traffic controllers have a set of paths. And so it creates this a parallel set of arches across the North Atlantic that stands out.
So it's not a big problem, correct? Because the area like we were talking about most in the
Yeah,
Southeast Asian countries.
well, it's a problem if you misinterpret them as boats. And so we're happy to get more information about anything that humans are doing out over the ocean. And so we don't look at it as a problem because we know what it is. It's not boats. But when it's mixed in, there are surely similar detections in other places, and they aren't there often enough to form a trace. For instance, we look at the Straits of Malacca. We see the routes, and I'm sure those are boats. Those are not aircraft.
Thank you very much, Dr. Chris. We have another question. I think it's from Anurag. I noticed that most of your data comes from NPP VIRS, PIRS. Do you know any other NTL-RS product or satellites that can provide data on color temperature or have red, green, and blue bands in nighttime?
Yeah, NOAA 20 and NOAA 21. And so our boat products and our Beers Nightfire, that runs on 3 satellites. And so SNPP was the original one, and it's kind of our go-to if we want an example. But there are 2 other Beers instruments that fly. They're staggered about 50 minutes apart from each other. And so right now there's 3 of them. And we download all the nighttime data from each of them. It's about 150 gigabytes a day, and run our algorithms through it. And there's a vast reduction in the data volume between the input and our final CSV or KMC.
Thank you.
But I'm not aware. There's a lot of other instruments that are polar orbiting, weather, or environmental satellites with coarse spatial resolution, but none of them have the low light imaging, and none of them turn on their daytime channels.
Okay.
I've talked to the operators regarding, well, you've got the same bands, but you don't collect at night with the near infrared or shortwave infrared. You've got the same bands as Beers, you don't collect at night. And they say, well, there's nothing to see. And to which I say, there's almost nothing to see. And so there's a little bit, and it's got a lot of information content.
Thank you, Dr. Case. So like the application side, if someone would like to work for a very small area, what do you suggest? Like we communicate with your group to collect the ROI data for that specific region, or we just can take the global data and crop it?
You know, for quite a few years, we've talked about having a web map service that allows you to cut out a little window from our global products. And we've never been able to pull that off. So right now, the best solution is they can download the global product and then zoom in on their area of interest, establish a rectangle that they want to extract. And it's cumbersome, but that it's it's not that hard to do.
Thank you very much. So colleagues, students, do you have any other question? If not, dear participants, I think those of you who are attending online, my colleague is going to share something. How are you going to do it with the participants here for now? Okay, but that can also be continued after the session, correct? Okay, so thank you very much, Dr. Chris, for the wonderful deliberation. I think we have a lot of information about these data sets and the applications and the possible application in different sectors. Probably those of us are really interested. We can directly communicate with you or communicate through the coordinators of this session so that we can make the connection to Dr. Chris. And I think Dr. Chris has already mentioned at the beginning, those of us are really interested about these data sets. We have this option to register, and probably we are going to get the information about the data almost every day. Okay, so my colleague is actually requesting that every one of you, please, if you can join this evaluation of this session, that would really help us a lot. Mr. Borabet, would you like to say anything?
Thank you, Chris. Patient content. I know that you content for me.
So thank you very much. Thank you, everyone. Thank you, our participants who have joined here physically and all of our participants who are joining the Zoom session, Zoom link through the Zoom link. Please, we request you again to join the evaluation of this program. So you can just scan the QR code or go to the link and do this small evaluation. That will help us a lot. So with that, once again, we like to thank and convey our sincere gratitude to Dr. Christopher T. Elvis, coming from Colorado School of Mines. And we hope that you will continue teaching the course that you have started in January semester at AIT. I just have heard that next year you are going to offer the same course at AIT. So our students will have the opportunity to learn about this specific topic in remote sensing. And probably many of them will take it forward and really apply into their research. So with that, I think once again, I like to just bring this information that this hybrid seminar or lecture actually brought to all of you by IT Extension in association with Uniter CIPAL. And it is our great honor and a privilege to have this session delivered by Dr. Christopher D. Elvis. I think you all know that AIT Extension and Uniter CIPAL is bringing many of this kind of online free sessions for students, AIT students, for staffs, and actually audience from all over the world. We are trying to communicate through our network, and that is actually on many different topics. Like we had one such session yesterday, and probably one session is going to be tomorrow. So I like to request all of you, if you are interested, please keep an eye on our website and the social media sites of AIT Extension. You can get all the information on what's coming up. But of course, probably you all know that the AIT Extension and the Uniter CIPAL are also mandated to design and deliver training programs, which could be technical training, managerial training, and the training for many different sectors, many different audiences. So with that, I like to request all of you to keep an eye to our website, to our social media sites, and also you can feel free to communicate with any of us. I think with that, we are going to end this session. And if you have any other queries, any other request, or if you also like us to bring some other topics in future, you can feel free to contact us. So thank you very much. Thank you, everyone. Have a great evening, great afternoon. Do we have a question or? Okay, I forgot to mention that, yes, those of you have already registered in this session. everybody are communicated by email. I think you are receiving our email. The same way you will receive the information about this session, including the evaluation, sharing the presentation and other information. We'll be doing that. So don't worry about that. Yeah, Kona would like to. Okay. I thought the Q&A session is over. But sorry, Mr. Anurag. I think Dr. Chris, can I request you to answer? There is one last question. So this question is again from Mr. Anurag. And the question is from the issue of interactions with air and light pollution, is it possible to measure the PM 2.5, particulate matter 2.5, in nighttime scattering from the artificial light as seen in the satellite imagery? So he's talking about this issue of air pollution. Yeah, please.
I've seen evidence for that. And for instance, China has a lot of aerosol. And I've seen images that were collected either moonlit or new moon, where you can see this fuzz. It's like this layer that is making the lights a little fuzzy and scattering. We haven't done anything with it, but I think I've seen a few papers. And that's one more thing I'll say about one of the good aspects about making global products and making them free and no copyright and easy to find is that it's really launched my publication records, my citations. Over 30 years, it's gotten substantial. But yeah, there is something going on there. And so we're currently working on developing an algorithm to discriminate sharp lights from fuzzy lights. And so hopefully we're going to have a student working on that this summer.
Thank you very much. So thank you, Mr. Anurag, for bringing this issue. This is also a big issue for Bangkok and the neighboring cities. In Thailand.
In
And
April.
Right now, we are actually talking a lot about this. You know, whether our children should be out to do the outdoor activities or not, and all those things. So this is
Yeah.
become a big issue.
Well, you know, it could be investigated because we have our monthly cloud-free composites that we make. We filter out moonlight and clouds and sunlight as best we can. And there's a whole time series. And so there's one each month. And so you could look at January versus April. And maybe there's something there that you can see that the lights look a little fuzzy, a little less sharp in the months that you have your big smoke problems. So we do have data that could be used to study that.
Thank you very much, Dr. Case, once again. Thank you, everyone. Thank you for joining the session.